Okay, my name's Kevin Andrew from the University of Victoria, and this is my contribution to this year's CPEG virtual conference. I'd like to thank the organizers and the scientific committee for giving me this opportunity to create this video and to share my research. Um, I'm working on an updated draft of this paper, which is called R&D Spillovers and Productivity, the Importance of Heterogeneity. And so hopefully by the end of the month, this draft, including the numbers that I'm presenting today, will be available. Um, you can go to my website, kevinandrewecon.ca. That's where it will be, as well as these slides and a link to this video. So the motivation for this work is a large literature in economics on R&D spillovers. And this is important from a policy point of view because pretty much the majority of advanced economies subsidize research and development expenditures in some way. So a recent study by the OECD shows that 30 out of 35 OECD countries and 21 out of 28 EU countries provide some form of either preferential tax treatment, tax relief, or subsidy or something like that for R&D expenditures. Now, the reason for this is well known. It has to do with spillovers. The theoretical justification being that if one firm does some R&D which benefits another firm, and they aren't able to, internalize all of the profits from that innovation, then there's going to be an under provision of R&D and innovation services in the economy. And there's a large body of empirical work which has in fact identified these positive spillovers using what's called the knowledge capital model, which was spearheaded by Grillickies in the 1970s. And that literature, I provide a citation here, is summarized in Hall, Morese, and Monin in 2009. And the overwhelming conclusion is that there are in fact positive spillovers to R&D across firms, therefore providing a justification for these policies. And there's also convincing policy evaluation evidence that's summarized in Bloom and Van Rieden recently in the Journal of Economic Perspectives, which shows that these R&D subsidies do, in fact, have their desired effect of raising R&D expenditures. So now, what I'm really interested in, though, is the fact that some economies, they target their R&D tax credits at small and young firms. So the subsidy is not linear. It depends on the size or the age of the firm. And this is prevalent. 11 of the 30 OECD countries have some form of this going on, and Canada is one of those countries, as we provide an enhanced tax credit to small and medium-sized firms. So what I do in this paper is I use data on US publicly listed firms from CompuStat, and what I do is I identify R&D spillovers and show that they're heterogeneous with respect to firm size and age. Okay, so the way that these spillovers affect firms is different depending on how old they are and how big they are. And the answer is that as firms get older and bigger, the impact of spillovers on their productivity shrinks. Okay, so young firms and small firms benefit more from R&D spillovers is the conclusion of this paper at this point. So the model that I'm going to use here, I follow a recent paper by Ulrich Dorzelski and Jordi Geomandru from 2013. And different from the knowledge capital framework, they estimate a production function, which is relatively standard, and they assume that productivity follows what's called a controlled Markov process. So this is like an AR1 on steroids. So the idea is that mu, I'm going to call this the conditional mean function. So the mean of next period's productivity depends on lagged productivity, as well as the firm's age, their R&D spending, and the size of what I'll call the spillover pool. I'm going to tell you exactly how I measure this spillover pool later, but you can view it as some aggregate measure of all of the R&D or innovation activity of firms in related industries. Okay. So, Z prime represents productivity next period. So productivity next period depends on all these different factors. Okay. And what I'm going to do is I'm going to work on an estimation strategy, which is going to back out this relationship. Okay, and what I'm interested in are the cross partial derivatives um, of uh, of this conditional mean function. So when I say nonlinearities with respect to R&D spillovers, these are exactly what I'm talking about. Okay, so this one here is the cross partial between productivity and spillovers. So do firms with higher productivity benefit more from spillovers? The answer is this cross derivative. Okay, do older firms benefit more or less from spillovers? The answer is this particular cross derivative. Is there a complementarity between firm A's R&D spending and the spillover pool? Well, that's the point. That's what's identified here with the third cross partial down here. Okay, so essentially, once I've estimated this conditional mean function flexibly, I can answer questions about the signs of these cross partials. Okay. So my estimation strategy follows the recent literature on production function estimation. In particular, kind of the first generation of these papers followed Ollie and Pecos and Levinson and Petrin. But more recently, some issues around identification have been raised by Ackerberg, Caves, and Fraser, as well as Gandhi, Navarro, and Rivers in an influential paper. And so my approach is going to be immune to the critique of Gandhi, Navarro, and Rivers based on an auxiliary assumption I'm going to make about returns to scale. Okay. So, however, following Levinson and Petrin and Ollie and Pecos, I estimate a first stage, and this is the purpose of the first stage is to deal with the endogeneity of productivity. So, productivity is subsumed in this non-parametric function phi here, and so essentially what this first stage does is it separates epsilon, which is not endogenous, from the part that is endogenous, which is Z, total factor productivity. And then in stage 2, I can back out Z conditional on the parameter estimates for theta K and theta C. So I don't actually know theta K and theta C, but if I'm willing to make an assumption about what they are, I can back out a value for Z and then use this Z to estimate this controlled Markov process. Remember, this function here is the thing that I'm actually really interested in. So here's where I back that out. Okay. Now, importantly, once I have estimated that conditional mean function, I can recover the residual from it, which is going to be orthogonal to anything in the time t information set of the firm, which is going to, in this case, the only thing I really need, because there's only going to be one parameter, is going to be lagged capital, which is definitely in that information set. Okay. Now, the reason why there's only one parameter is because I assume constant returns to scale. So the strategy I take is to assume a returns to scale and then check the robustness to it later. Now, I'm not going to talk about that robustness in this short video today, but that's my strategy. Okay. And this deals with the Gandhi, Navarro, Rivers critique. Okay. The one variable which I need to talk about how I empirically construct is the spillover pool. So how I need to determine how close two firms are in technology space or innovation space, if you will. And the way I do it is by constructing a vector here, which is kind of like the innovation profile of the firm. So when a firm takes out a patent, they have to they have to say which category it's part of. And there's 426 categories. So each of these S's represent the share of firm I's patents that are in category 1, 2, et cetera, okay? And the idea is that this omega ij is essentially the correlation coefficient between these vectors for two firms, right? So if firm I and firm J have very overlapping technology profiles, then this is going to be a higher number. And if it doesn't overlap at all, it's going to be a very low number. Okay, so in this sense, if two firms take out similar proportions of patents in these subcategories, they're going to look very similar and they're going to be very close together. Okay, and then I use this weight to aggregate up some measure of innovative activity at that firm. The measure I choose to use is actually the stock of knowledge capital. And in constructing this, I follow the best practices from the knowledge capital literature that is summarized in that Hall et al. 2009 paper. And so I construct a spillover pool. I use a perpetual inventory method to create a stock of knowledge capital, which I then aggregate. And this leads to good year-to-year and across firm variation in this aggregate measure of R&D, the spillover pool, if you will. So I'll just quickly have a look here at the summary stats. I want to point out just a couple things. First, these firms are big, okay? The median sales are 77 million. Those are big companies. And all of these variables are incredibly rate skewed. So the means are always greater than the medians, you'll find. Secondly, there's just shy of 1,500 firms, okay? And the data runs from 1977 to 2010. So I have an unbalanced panel. At this point, I'm not dealing with exit. There are ways I can do that in future iterations of this paper. And all of these variables, except for age, are measured as millions of 2012 US dollars. Age is age since listing on the stock market. I don't have the age I don't have the age that the company was like founded, for instance. I only know when they list. And lastly, mergers and acquisition activity. The data has been cleaned of that. So if there's been mergers and acquisitions, I drop the firms. So this is a clean sample with regard to that. So here's the first part of the results. First, remember I've imposed, okay, I'll talk about, sorry, these columns. Column 1 is a version of the model where the conditional mean function here is linear. And in 2 and 3, it includes some nonlinear terms. So that's the difference between 1 and 2 and 3. 2 follows my identification strategy, and 3 is OLS, okay? So I did it by OLS, and then I also followed my identification strategy just to see, if the results were making sense. And the good news is that I think they do make sense. There's a few differences, but for the most part, I'm happy with these elasticities here. Notice that there's definitely some bias because the capital elasticity goes up when we account for account for endogeneity. So there's definitely a correlation between capital and the error term in OLS. Okay. Now, if we look first at just the linear version of the model, first of all, productivity is very persistent. It's so persistent that from now on, I'm also going to refer to it sometimes as firm size, because if productivity is really, really persistent, then it's going to be highly correlated with capital and the number of employees. TFP grows over the life cycle. The marginal effect of $1 of R&D is actually negative, which was surprising to me. And the spillovers are positive. And if we look at the number of zeros here, for the standard errors, they're statistically significant. Okay. Now the magnitudes here, I wouldn't read too much into them. They're elasticities. So what this says is that a 1% increase in the spillover pool would lead to a 0.0013% increase in productivity next period. But remember that productivity is then capitalized in this firm for the rest of the firm's life, right? So even though these numbers appear small, they could be quite substantial. I'm going to need to think a little bit more about how to present these results in a way that kind of quantifies just how important these spillovers are. But for now, I'll just talk about their signs and whether they're statistically significant, okay? And then when we include the nonlinearities here, I'm not going to focus in this case so much on this table. I'm going to go to the next slide where I show you the nonlinear terms, okay? So these mu ZA, that's the cross partial between Z and A. Here's the cross partial between Z and R, et cetera, et cetera. Let's focus on the ones that have to do with spillovers, okay? And if we see here, the top panel represents my estimation strategy. The bottom panel represents OLS. And what we find here, the negative with respect to Z and with respect to A is consistent across both. So the magnitudes are certainly differ, but the sign and the sign is definitely the same, and there's at least some statistical significance in all cases. The only one where it's maybe not very significant, I believe this one's significant at the 10% level, but not the 5% level. Okay. Now remember, I have a very limited data set, short panel, 1,500 firms, et cetera, et cetera. So, I'll have to investigate that a bit farther, but, I'm going to go ahead and say that I identified these negative cross partials and that I need to think a little more seriously about what their magnitudes imply. Okay. So what do we have here? We have a negative complementarity between spillovers and firm size / productivity. We have a negative complementarity between spillovers and firm age, and we have no complementarity between R&D spending and spillovers. So what does this mean? Well, I'm going to leave that for future work or the future development of this project. So I've identified this idea that spillovers are not necessarily uniform across the firm size and age distribution. That's what I've identified. So the question then becomes, A, are the nonlinearities that I found quantitatively important? And that might depend on the question that we're asking. So that's the first question I have for myself. And the second question I have for myself is, what are the implications for the optimal design of an R&D subsidy or tax policy? Okay. And I can't do that without maybe putting a little more structure on this model. So the beauty I think the elegance of this approach is that I actually made minimal assumptions to identify this process, which is incredibly flexible for productivity. This really flexible process can be used to identify interesting nonlinearities. However, in order to say things like about the welfare implications of this and the optimal design of tax policy, I'll have to put this into more of a quantitative model. I came at this, I'm a macroeconomist, so I have an idea of the type of model that I'll write down, and I'll have to evaluate different types of R&D policies, and I'm particularly interested in nonlinear policies with respect to age and size. Okay, so there has the potential to be really interesting policy design implications here that maybe I don't fully understand yet. And I'll hopefully start to understand them better as I come to interrogate these results a bit more. But I am really interested in the optimal design of R&D subsidies. Okay, thanks for listening.